Okay, so today we're going to be talking about compilers. A compiler really has two main parts, the front end and the back end. The front end is probably the easiest to understand. It's also the thing that differentiates different programming languages. The main goal of a front end of a compiler is literally to take the bytes or string from a file and then turn it into intermediate codes, or IR. That's actually it. And what the heck is IR anyways, or intermediate codes? Well, all it is like a machine-independent machine code that can be targeted and then turned into multiple different machine code types. So instead of targeting specifically x86 or x64 or ARM or RISC-V, you could just target LLVM-IR, and then the LLVM-IR will then get turned into all these different types of machine code. Hopefully that makes sense. The backend, literally all it does is it takes the IR, optimizes it, and then turns it into machine code for specific platform and architecture. That's literally it. So front end turns code into IR, back end turns IR into machine code. That's it. That's the pipeline. Now in the last video, I might have been vague with my wording, so I'll just make this clear now. Binary formats are tied to the platform, not the architecture, which means binary formats are for a specific operating system and not the actual instruction set for the processor. Somebody called me out on that, said I was not being clear with that, so now I'll be clear here. Oh, also, the instructions within the executable are architecture dependent. The actual registers and instructions used are dependent on the processor. Hopefully that's also clear now. Now the front end of a compiler can be broken up into like 4 parts, that being lexical analysis, syntactic analysis, semantic analysis, and then converting whatever's left over from that to IR. The backend can be broken up into 2, maybe 3 parts, depending on the implementation. IR optimization, IR to assembly, assembly to machine code, and then linking, and then potentially some architecture-dependent optimizations after that. The final result is an executable that can actually be run on a computer. All right, so now let's go kind of more in depth on each part of the compiler. So we'll start with the front end. We'll start with lexical analysis, and I believe I might actually, by the time I post this, we'll have a video already out on lexical analysis. Should be pretty descriptive on the topic, but lexical analysis is the first step of any compiler or interpreter, and the goal of it is just to convert text into tokens. The text is usually read from a file, from disk, and the lexer will scan through the input character by character to derive meaning from the text. It will group together characters that follow certain patterns and then create substrings, and these substrings are then labeled, and the labels along with the substrings are called tokens. This step in the compiler also skips irrelevant characters such as white space, comments, and it also possibly stores additional information for error messages in the future, like keeping track of line and column numbers for each token. The next step is syntactic analysis, or parsing. And the goal of the parser is to simply take a sequence of tokens produced by the lexer and then convert it into some sort of structured representation, typically a syntax tree. But it could also be a stacked-based structure as well, as is the case with forth. Tokens are passed to the parser, which then checks if the tokens are arranged in an order that matches the syntax of the language. So if you've never taken data structures or you're confused a little bit, a tree is just a structure with data and then pointers usually pointing to multiple different other types of data. And each of these structures are called nodes. And so if a node has data and it has pointers to multiple different pieces of data, that's having multiple different children. And that's what makes it a tree, is having multiple different pointers. Otherwise it'd be a linked list. This is also, it's basically it's a directed graph, I suppose you could say. It's only unidirectional, it's not bidirectional, because if it was, then at that point we're talking about a graph. Semantic analysis is where you make sure the program makes sense beyond just the syntax. This step in the compilation process checks if the code is logically correct. This prevents type mismatches, the use of undeclared variables, variable redeclaration, variables used outside of scope, supplying incorrect arguments, improper return values. All of these things are under the umbrella of semantic analysis. And really the main goal of semantic analysis is just to catch any errors that got past lexical analysis and syntactic analysis. Lexical analysis would have rejected illegal characters, and syntactic analysis would have rejected an invalid ordering of tokens. Semantic analysis catches every other error. Now, all of these errors get caught using something called a symbol table, which just records the names of identifiers, type information, and scope. After we do this, we want to traverse the AST, convert the nodes into IR, and IR is just a simplified version of the source code, making it easier to work with, optimize, and convert into actual machine code. And you can sort of think of it as platform and architecture independent machine code. With IR, you can focus on just the IR and the target machine instead of the entire compiler pipeline. This allows you to target multiple architectures easier. After converting to IR, we might then optimize using a bunch of well-recognized optimization algorithms. The next step after that would be code generation, and this usually involves converting the optimized IR into assembly, doing additional machine-dependent optimizations, and then using an internal assembler to assemble the assembly. This usually produces an object file, which then an internal linker will be used to link the object file into an executable. And of course, this is all implementation dependent. You can skip any of these steps, combine some of these steps, or only do some of these steps depending on how you decide to implement your compiler. At this point, the program is fully compiled and ready to run on a CPU. All right, let's make a little bit of a distinction between interpreters and transpilers. They are similar to regular compilers, but they're slightly different. Interpreters don't generate machine code, they only execute the AST or the IR directly. It may involve JIT, just-in-time compilation, or internal VMs, but at the end of the day, it is just executing code directly without producing a program that you then run on the system itself. Transpilers convert code from one language to another, so a really common example is TypeScript to JavaScript. Pretty much the only difference is that instead of targeting IR or a specific platform and architecture, you're just targeting a different language entirely. So that's pretty much it. That's the phases of a compiler. That's how they work. That's their goal. Hope this was helpful. We can maybe go into some of these concepts more specifically and see how they work in practice. But thanks for watching. Hope you learned something. See you soon.